Good afternoon, and thank you for the talk. It's pleasant, and I'm grateful for being here. So I'll be discussing about entanglement and secret key agreement capacities of bipartite quantum interactions and read-only memory devices. This work is done in joint collaboration with Stefan Beumel, who is presently at Delft University of Technology, Netherlands, and my PhD supervisor, Mark Wilde. So first, why this topic? So bipartite unitary interactions are most elementary many-body interactions, and due to unavoidable interaction with environment, it is like study of these noisy bipartite interactions is pertinent. So what do I mean by bipartite interactions? So consider that you have two systems, A prime and B prime. They are input systems and systems of interest. They are in presence of Bath system, which is E prime, and due to underlying Hamiltonian, you have some unitary transformation, and that is how you transform evolve to system A, B, and E. And this, so now before interaction, we assume that composite system A prime and B prime, it is in tensor product and uncorrelated with Bath system. And after transformation, you get this state rho A, B, E, and it may happen that Bath is inaccessible. And because of that, then it becomes, so what we want to study is noisy interaction, where you have two input and two outputs. So mathematically speaking, these are called bipartite quantum channel, where you have two input and two outputs, and they are completely positive trace preserving maps. So when A prime system, A prime and B prime are inputs here, and when A prime and the output A is held by Alice and B prime and B is held by Bob, we call this as bidirectional channel. And this is, it corresponds to noisy bipartite interactions. So for all input state omega A prime and B prime, you can write it in terms of like below, that unitary is acting on Bath system as well, but you trace out degrees of freedom that is inaccessible to you. So motivation for it is that bidirectional channels, they form simple model for network, where you have two clients, Alice and Bob, and you allow communication between Alice and Bob, both forward and backward. Yeah, okay. And also like model for quantum gates, if you are looking at noisy intermediate scale quantum computers, then they will be noisy. You won't have clean CNOT gate or swap or any unitary like these gates, but you will have some noisy version of that. Then for entanglement may increase, decrease, or need not change in presence of these bipartite quantum interactions. So the two important tasks or building blocks of quantum information processing are entanglement, like the first is entanglement distillation, because we want pure entangled state in the end of protocols, or that is desirable. And by these are like useful resource for several information processing tasks, be it quantum key distribution or quantum teleportation. And then another is secret key distillation. Like, okay, so the conference is on quantum cryptography, so it may be one motivation. And this is for need of, for secure communication protocols between two parties over network. And another application is, are there possible any other secure communication protocols? So in this talk, I'll be discussing about private trading, which is new protocol that we introduce in this paper. So goal of this talk is to introduce two different information processing tasks relevant for bidirectional channels, like which is entanglement distillation, meaning that we want to generate singlet state or Bell state from two separated systems, and it will happen when we allow interaction between these two separated systems. And then second is secret key agreement, which is generation of maximal classically correlated classical correlation between two separable systems, such that there is no correlation with Bath. And then new secure communication protocol between two parties called private reading. So you can think of reading as like if I want to read CD or some memory device privately from librarian who is eavesdropping. So that is private reading. Okay, so terminology that we'll be using is like, so in this talk, I'll be giving upper bound on the capacities, like at what rate can you distill entanglement or secret key from bidirectional channel. And we look at the finite uses of channel, because in lab or experiment, we are only allowed like finite number of times, not infinite. So non-asymptotic capacity of channel for any given task is maximum rate at which you can perform or given task can be accomplished by allowing only finite uses of channel. Okay, so for secret key, so you allow LOCC operation between two parties, and using LOCC, which is local operation and classical communication, you can generate separable state, and then you have two inputs. So A is for Alice and B is for Bob. They are input to this bidirectional channel. LA1 is reference for Alice and LB1 is reference for Bob. And then you allow, so the most general possible protocol is when you allow for adaptive strategy or assistance by LOCC, because entanglement doesn't increase under LOCC. So we allow for adaptive strategy that is assisted by LOCC operations. And you allow, so we do this finite number of uses of channel, and in the end, you want, okay, so in the end, you want to generate secret key like MA and MB, so that you want to have secret key in the end. So it is, so we call this capacity as LOCC, assisted bidirectional secret key agreement capacity, and we will denote it with P. 2 is for input and 2 is for output. Since we are allowing for assistance of LOCC, that is in subscript, and it is for bidirectional channel that has 2 input and 2 outputs. So we introduce an entanglement measure of bidirectional channel that we call as bidirectional max relative entropy of entanglement. And here, so in this measure, you have supremum over pure states. Alice and Bob, they are in product state. And then you calculate max relative entropy of entanglement of the output state. So it suffices to allow for the reference system on Alice and Bob's side to be isomorphic to the corresponding input size. So this is definition. And then this is theorem that we have. So the key rate, maximum key rate that you can achieve is upper bounded by bidirectional max relative entropy of entanglement of the channel. And the second term is with error, like epsilon is error. And then we can also show that this entanglement measure is in fact strong converse bound, meaning that if you want to achieve rate above this bound, you will be getting error close to 1. You will reach to error close to 1 exponentially. So how do we arrive at, so how do we arrive at this bound? So the proof outline is due to so private states are states that contain log 2 k private bits. And this was introduced by Horodesky and Oppenheim in 2005 and 9. So the success probability, so we say that, okay, you have distilled private, secret keys generated in the end of the protocol when you have state omega and you project it on private state, and the trace is greater than or equal to 1 minus epsilon. And due to Horodesky's and Oppenheim, so we have this result that projection on private state with, and if we have separable state, sigma is separable state, then it is always less than or equal to 1 by k, where k is log private bits. Yeah. So the main observation is that amortization, or it is, so sigma is output state here, and rho is input state. So what it is saying is that the difference of entanglement between output state and input state is always upper bounded by the entangling power of bidirectional channel. So using these results, we can arrive at that theorem. And one thing to notice here is that if in any of this bidirectional protocol, you take A1 prime, if you take B1 prime to be trivial and A1 to be trivial, then this is single input and single output protocol that we had heard in, yeah, so that is point-to-point protocol that we generally look at. Okay. Yeah, so now coming to how much entanglement can, so the next question is how much entanglement can we distill from these bidirectional channels? So here, the most general way is that you allow for PPT assistance, where PPT is positive under partial transpose. And so adaptive channel here is PPT preserving, that the channels which preserve positive under partial transpose of state. And LOCC is one example of PPT preserving channel. So in this case, we introduce another entanglement measure, which is bidirectional max range information, which is an SDP, which is a SDP program. So you minimize over tracing out output of A and B, and V and Y are positive semi-definite operators. And then you take partial transpose on Bob's side. So difference of V and Y should be greater than equal to Choi operator. So Choi operator is a normalized entangled state when you pass through bidirectional channel. And this is efficiently computable. You can compute it using programming efficiently. So here, the bound is, okay, so you can show that the rate is upper bounded by max range quantity for bidirectional channel, and in fact, this is also a strong converse bound. Now, one application of bidirectional channel is private reading. So that is like, let's say if I want to read memory device, that is called reading protocol, which was introduced by Bose and others in 2000, and then Pirandola in 11 for noisy channels. So here message is encoded in terms of quantum channels chosen from set. We encode message M into code words from X1 to XM, and then set device accordingly using these channels. So for each classical bit, you have a channel. And then Bob can enter quantum states and perform channel discrimination kind of task to learn what the message is. Now, this is how you can understand how do we read a CD or any memory device in computer or some reading. Now, since N is noisy, so there may be loss that goes to eavesdropper. So next question we can ask is that, is there any protocol for secure reading against eavesdropper? And this is what we call it as private reading. So here, so we consider memory cell, which is wiretap. That is, you have input is B prime, and it goes to Bob and eavesdropper. And then the size of B prime, B and D is independent of X. And we saw that in non-adaptive strategy case, you can achieve, and also this is the capacity. So which is mutual information of, difference of mutual information on the Bob side and eavesdropper side. Yeah, so we also have, yeah, and then we can also give upper bound on private reading capacity when we allow for adaptive strategy, and that is given, so private reading or reading protocol can be understood as one instance of bidirectional channel. And this is, so we leverage bound from secret key agreement of bidirectional channel to give upper bound on private reading when it is isometric wiretap memory cell, meaning that you have, okay, so U is unitary here, and then you trace out the part of eavesdropper, and that is upper bound. Okay. So conclusion is, in this paper we derived upper bounds on entanglement generation and secret key agreement capacities over bidirectional channels. Sizes of reference systems are same as size of input systems, and this question was open in Bennett et al. In 2003 since then. We can also achieve, or we can also derive tighter upper bounds, which is derived in paper for channels obeying certain symmetries. Then introduced secure protocol for reading of memory devices under scrutiny of eavesdropper. Both upper bound and lower bounds for this protocol can be found in, this is reference. And here, this is SDP program where we have calculated bidirectional max range, like how much upper bound on how entanglement distillation rate for bidirectional channel. So just to show that, so this is for collective dephasing channel and swap operator. So, so these, not all rates are achievable here, but for two, it is indeed achievable, and others are just upper bound. Okay.
Okay, we have time for questions. Okay, seems no one has questions, so let's thank the speaker again.